afternoon, everyone. It's my pleasure to introduce today's speaker, Professor David Randall from the Department of Atmospheric Science at Colorado State University. David has undergraduate and master's degrees in engineering and then went on to do a PhD in atmospheric science at UCLA. He worked for a time at MIT and NASA before taking up his present position at Colorado State in 1988. He is a Fellow of the American Meteorological Society, a Fellow of the American Association for the Advancement of Science, and a Fellow of the American Geophysical Union. He's also a past recipient of the American Meteorological Society's Meisinger Award. And so it's a great pleasure to welcome him to SFU, and please join me in doing so.
Thank you, and thanks very much for the introduction, or for the invitation. I'm very happy to be here. So I've made a little outline of the talk. It's got three parts with somewhat indistinct transitions. So I'm going to start by talking about a very simple perspective on climate change, which take about 10 slides or so, many of which will go very quickly. And then I'll work my way into a discussion of comprehensive climate models. This is part of what I was asked to address here. So I'm going to actually talk about all the different components of the models, but my own specialty is the atmosphere. And so when we come back at the end of that, I'll be talking about feedbacks that work in the atmosphere. I'll also talk about one other one. So the emphasis is going to be on feedbacks involving clouds and water vapor. And these feedbacks are important because it's expected that they will increase the magnitude of the climate change by something like a factor of 2. Climate change on the back of an envelope. So I want to start by asking you, and you don't have to answer me out loud, but you can if you want to, why do we think that more CO2 will make the climate warm up? Or maybe you don't think so, but why do we, in some generic sense, think this? Is it because we see an increase in the amount of CO2 in the air, and we see an increase in the temperature of the air, and we say, oh, this curve is going to do that? No, that's not the reason. Is it because we have computer models like the ones I'll be talking about in the middle section of the presentation that run on big machines like this one called Jaguar at Oak Ridge, Tennessee? No, it's not because of that. It's a lot simpler, really. The climate system does what it does because it's heated. There's a pattern of heating and cooling. If you change the heating, you change the climate. And this is basically why we expect a climate change in response to increasing greenhouse gases. So I don't want to offend anybody with the simplicity of the slide, but this is the basic energy budget of the Earth. Here's the Earth. This is the sun over here. It's actually somewhat further away than what you see in the picture. Solar radiation incident on our planet, and part of it's being reflected back to space. The fraction that's reflected is called the planetary albedo. It's about 0.3. And then the Earth itself emits energy to space, and not just in one direction. This makes it appear that it's being emitted that way, but it's really being emitted essentially in all directions simultaneously. So the sun's coming from one side, and the Earth is emitting in all directions, and I've just lost my battery. And these flows of energy can be measured using satellites like the one shown here. This is the Earth Radiation Budget satellite launched from the Space Shuttle, actually, back in 1986, and other satellites like it. So we have pretty good quantitative information about these flows of energy at the top of the atmosphere now. So I've got two slides with equations here, and then there won't be any more. Actually, really just one, because the second slide has numbers on it. But let's think about, here's the Earth again, and it's absorbing and reflecting. Here's the incoming solar, here's the reflected part, and this sort of orange circle represents the emitted infrared. And we're going to think about the Earth as if it was a point characterized by a single surface temperature called Ts. And what I'm writing here in this first equation is a simple version of the planetary energy budget. So S is the amount of sunlight coming in from space. It's the energy per unit area per unit time. It's about 1,365 watts per square meter. Pi a squared is just the cross-sectional area of the planet, where a is the radius. And then this parameter alpha is the albedo that I mentioned before. It's the fraction of the incoming solar radiation that's reflected back to space. So 1 minus alpha is the fraction that's absorbed. So this side of the equation is the absorbed solar. And the opposite side, the other side of the equal sign, is the emitted infrared. So this equation says the two are in balance. And of course, they're not perfectly in balance. But actually, if you go to the satellite data that I mentioned a minute ago, the imbalance is small enough that it's not actually detectable. So we can't distinguish the imbalance that we have from zero based on the data that we have now. Although there is another way to do it that I could mention if there's a question about this later. So on this side you have, and I really have a problem, I'm going to go to the other pointer. This is the emission from a black body, Stefan-Boltzmann constant, temperature to the fourth power. We're just using a single sort of average surface temperature, and it's important that it is the surface temperature, okay? This is not the temperature up somewhere in the middle of the atmosphere. It's the surface temperature. And then 4 pi a squared is the area of the sphere, so we're treating this emission as happening at every point on the sphere, as I mentioned before, like this orange glow. And then epsilon is a parameter that represents the bulk emissivity of the planet. It's a number between 0 and 1. If it's 1, it means the Earth emits as a black body at that temperature. If it's 0, it means the Earth doesn't emit at all. The actual number is around 0.6 or so, a little bit more. And so roughly 60% of this black body temperature gets out to space. And these two things are very nearly in balance. So you can cancel out pi's and a squares and so on in the first equation, and you end up with this. And now what I'm going to do is Calculus 101. I'm just going to differentiate it, and I'm going to make some assumptions, which are actually stated here. So first thing I'm going to do is assume that the system is perturbed, but the only perturbation is a change in the amount of CO2 in the air. And what that will do is change the bulk emissivity of the planet, because it makes the atmosphere either more opaque or less opaque. If we increase the CO2, the atmosphere is more opaque. Epsilon goes down. So we're going to have a delta epsilon right there, and it's a negative number, because we're going to increase CO2. And then we're going to allow the temperature to change, of course. So there's the change in temperature, and you can see I've differentiated that. I got 4 sigma T cubed delta T. And on the left-hand side, we just put the perturbation to 0, because we're going to treat the sun as not changing and the albedo is not changing. So I put no feedbacks in red here, and what that means is actually several things. No change in the albedo due to melting ice or snow. No change in the albedo due to changes in the clouds or changes in the vegetation. Nothing like that. So the albedo is just assumed not to change here. And I'm also assuming that the only change in epsilon is due to doubling CO2. It could also change due to a change in the amount of water vapor, or it could change due to changes in the clouds. And let's just temporarily assume that that doesn't happen. The only thing changing is CO2. So I can solve this little equation here for delta Ts, and I get this. So it's proportional to minus the change in the emissivity. Remember, the emissivity goes down when I increase CO2, so delta epsilon's negative. This is going to be a positive number over here. So let's go to the next slide, and what you're going to see at the top of the next slide is the same equation repeated. There it is. And we'll put in some numbers. So the actual emission from the planet today is known to be roughly 240 watts per square meter. And we also know that given the surface temperature of the Earth, if you change the amount of CO2 in the atmosphere, if you double it, you'll produce about a 4 watt per square meter change in the outgoing long-wave radiation. That's basically spectroscopy. So I can take the ratio between these two and get delta epsilon over epsilon, and it turns out to be minus 4 over 240. Now, the other piece of information we'll put in from observations is the globally average surface air temperature is 288 Kelvin. So we get, putting in the numbers here, basically minus 4 over 240 right there, and minus 288 over 4 right there, and we get 1.2 Kelvin. So that's the change in the surface air temperature that you would expect to get if you doubled CO2 and nothing else changed, no feedbacks of any kind. And let me just point out before we leave this slide that the change in the emissivity, or the fractional change in the emissivity, or the fractional change in the outgoing long wave is roughly 2%. And the change in the temperature is roughly 0.5%. We don't normally talk about temperature changes in percent, but of course you can. This is absolute temperature. So this number is not particularly weird compared to that number, okay? If I got a 2% here and a 20% here, you'd wonder what was going on. But that's not what happened. Given this very simple physical picture, it would be very surprising. Yes? Well, because the emissivity is measured in terms of the infrared radiation flowing across the top of the atmosphere, and the black body radiation is at the surface. So in between I have an absorber and an emitter. So the photons that I see coming out the top have been interfered with by absorption, and then there's emission from the cooler air above. So what you see coming out the top is lower than what you would get from the black body at the bottom of the atmosphere. So given this simple picture, if we didn't see any warming of the climate, you'd wonder why not. To go any further than this, we need more comprehensive models. But before I start talking about more comprehensive models, let me just say that if you ask me personally, why am I very confident that our climate is going to warm up in the coming century? This is why, what I just showed you. This is why I believe it. So, top 10 things you need to know about climate models. And there's not going to be time to go into any detail here, but I'd be happy to take questions that want to probe down to some greater level of detail. First thing I want to list is just what are the major ingredients of such a model. There is and I'll talk about each one of these separately. There's an atmosphere model. There's an ocean model. The ocean is extremely important for climate. There's a model of the land surface. There's a sea ice model, which you could think of perhaps as being part of the ocean model, but it's a separate kind of physical problem. And then there's some machinery to couple these different pieces together, called the coupler. So the models are based on partial differential equations. I'm not going to go into any of that here, but I mean, for example, the Navier-Stokes equation is applied essentially as an average over a large box to describe the fluid dynamics of the atmosphere. I'll talk about the large boxes here in a minute. Spherical geometry for obvious reasons. We have to discretize the equations to solve them on a computer. So we're converting differential equations into finite difference equations or some other discrete form. The time steps used are on the order of a few minutes. So what we're actually simulating is weather. And we simulate a whole lot of weather and average it up, and that's climate. The same way you get climate from real data. And in order to do this, you need very fast computers. So, the atmosphere. This is about the atmosphere model. And, this could be the subject of a semester-long course, if not more. I hope you can read. I'm sorry that some of the colors are not appearing as well as they are on my screen. But we solve equations that express conservation of mass. And, of course, mass has different flavors. We're talking about dry air, which has an essentially uniform composition below about 80 kilometers high. That includes CO2, of course. Momentum, so that the winds. Energy, let's say in the sense of thermodynamic energy, so temperature, roughly speaking. Water vapor and other forms of water, like you see in this picture, are, of course, mass, too. So we have conservation equations for several flavors of water. And then things like carbon dioxide, methane perhaps, ozone, very important radiatively, and some models, other chemical species, sulfur species for aerosols and that kind of thing. So the atmosphere model will include at least these first four, and in more modern models now, all of these things too. The processes are listed over here on the right-hand side. So advection is a jargon. It means basically changes brought about by particles of air moving around, essentially the wind. So if cold air moves in from further north here in Vancouver, you'll say that temperature cooled off because of advection of temperature. Pressure gradient force, of course, important for predicting the winds. Rotation of the Earth, also very important for predicting the winds. Solar radiation, terrestrial radiation, the effects of turbulence on actually a range of scales. Moist convection refers to the kinds of things you see in this picture, growing cumulus clouds, thunderstorms, that sort of thing. Various processes that we call microphysics, which involve the growth and evolution of drops that become rain or ice crystals that become snow. And then there's momentum transfer. You can't read this, but it says momentum transfer by small-scale buoyancy waves. And I'm saying buoyancy waves here because what we really call them is gravity waves, but that sounds like something completely different. We're talking about waves that are produced sometimes by this type of cloud bumping up against a stable layer, but also by flow over the mountains. So a modern model includes all of these processes in some form for the atmosphere. The equations are solved on a grid. I'm showing you two different kinds of grids here. There are actually more than two, but this is a grid that's based on a spherical coordinate system, so it has a pole. This would be called longitude. This would be called latitude. And this is a grid that's derived by starting from an icosahedron and subdividing. And there are other kinds of grids out there. The ocean model, of course, also represented on a grid. So this list is the list of things that you would predict for the ocean model. Mass, again, of course, meaning mass of water. Momentum, so we're talking about ocean currents. The temperature of the water, the salinity, sea ice, of course, various chemical species of interest, and potentially ocean biology. This is just emerging now, but this is important for a variety of reasons. And here's the list of processes. You notice some of them have X's. So I basically copied the list from the previous slide to make the point that many of the processes that are relevant to the ocean are the same, like, for example, advection and the pressure gradient force. But the ones with X's are the ones that are not relevant. So terrestrial radiation, this means thermal infrared, is not important because the mean free path of an infrared photon in the water is essentially zero. Moist convection means thunderstorms. Those don't happen in the ocean, and this refers to clouds. They don't happen in the ocean. But the rest of the stuff does. Land surface. This is actually a very interesting subject. It's not my specialty at all, but I have good friends who specialize in this. So I deliberately chose a picture with lots of vegetation in it because the vegetation turns out to be extremely important for the interactions of the land surface and the atmosphere. The plants transpire water through the holes in their leaves called stomates, and this water is pumped up from underground. If the vegetation was not there, that water in the ground would have a very difficult time getting out. It would be basically leaking out through molecular diffusion, which is a very, very slow process. But the plants can pump it out a lot faster than that during the day when they're doing photosynthesis. So vegetation is important. Energy, of course, is always important. Water, obviously, is going to be important. Snow falls on the ground. You don't see any in this picture. But the flows of carbon are important, and the modern climate models now are actually trying to predict the evolution of the atmospheric CO2 content over time because it can be affected by things like vegetation on the land surface or the oceans. A little bit about the history of this field, because I'm assuming that many of you don't know about this. You can kind of trace this back to Richardson, 1922, Lewis Richardson, who proposed a kind of human-powered climate model, or actually a weather prediction model, What you see in this picture is a kind of auditorium, and these are rows of seats. And there are people sitting here doing arithmetic on hand calculators of some kind. And this is what we actually do using computers now. So he envisioned this thing as a human-powered computer that would run a model, essentially, like what we do today. And the way he formulated the model is amazingly similar to the methods that we actually use. Right after World War II, the folks you see in this picture, and especially Jule Charney and John von Neumann, got together at Princeton and applied digital computers, in particular ENIAC, to the problem of weather forecasting. And this is a kind of predecessor of today's climate models. 1956, Norman Phillips, who's actually right there, who's still alive, did the first global atmospheric simulation using a very crude model, but still, he managed to produce some features of the observed circulation. And then starting in the early 60s, and especially by about the middle 60s, a whole slew of people whose pictures are shown here began working in several different places, all in the United States at that time, building what we would call climate models. And so the first real global atmospheric models with representations of all the processes that I showed in the previous slides were constructed during the 60s, and also right at the end of the 60s, this guy, Kirk Bryan, built the first global ocean model. And Kirk Bryan and Suki Minabe, shown here, teamed up and coupled the two models together, and in 1969 published the first coupled ocean atmosphere global model. So that's really the beginning of climate modeling. And then, amazingly, it took until the late 1970s before models of this type began to be used for weather prediction. Of this type, I mean global. There were hemispheric models that were used quite a bit earlier, but the global models started in the late 70s in Europe. More realistic land surface models, including the vegetation that I described before, were constructed during the 1980s. And as you know, today we have this institution called the Intergovernmental Panel on Climate Change, which is putting out reports about once every 5 years or so. And that got started in the early 1990s. So today, depending on how you count, of course, there would be something roughly like 40 models worldwide. So there's a lot of different people and a lot of different places working on these things, and it goes back roughly 50 years. The models are tested in a variety of ways, listed here in sort of short form. First of all, the components are tested individually. So, for example, something like radiative transfer code is tested against line-by-line calculations, which would be much too expensive. And the line-by-line calculations themselves are based on spectroscopy, essentially. So you try to tie it back to your foundation data. Weather forecasting is done with essentially the same kind of atmosphere models, and in some cases also ocean models now, and land surface models. And so if you are going to make a climate change simulation and you use that model to do weather prediction, and you build up a large number of forecast cases and systematically evaluate the performance of the model, it's a way of testing it, and it's a pretty good way of testing it, actually. The errors that models produce in longer climate runs, like 100 years, tend to look similar to the errors that they produce, the systematic errors that they produce in the first few days of a weather forecast. That's very convenient. It means that by running the models routinely in weather forecasting mode, you can detect errors that will be important for the climate simulation. Of course, the ability of the model to simulate the current climate is an obvious test, and simulations of past climates. Of course, the data for the past climates is less complete and less reliable, perhaps, but it's an important thing to do, and the models are tested in all of these ways. They use a lot of computer power. I don't know what this guy is doing exactly, but this is an IBM Blue Gene machine. So just to give some rough numbers, something like 1 million floating point operations are needed to simulate one day. So if you do the math, it takes on the order of 10 to the 17th floating point operations per simulated century. And these numbers are going up because the models are getting finer grids and becoming more complicated and more complete. So these are just based on sort of typical models of the early 21st century. Since I was in graduate school, which was in the 70s, we've seen something like a factor of 10 million increase in computer power, which is pretty amazing when you think about it, although this little machine right here is several times faster than a Cray 1. And the Cray 1 came out in 1976, I think, and that was the supercomputer at NCAR. And, of course, it has a lot more memory. The Cray 1 had 8 megabytes of memory. And I think this has 4 gigabytes. And this costs less. But these machines are getting much harder to program. And the main reason for that is that you're using a very large number of processors trying to make them work together, and that's tough. Okay, so let me list a few things that are missing in today's models. And actually, many of these things, even all of these things, are being worked on at some level. I didn't mention the ice sheets on the continents. Here's Greenland. These are obviously important for sea level change on timescales of centuries, we hope. And those submodels are being added now. So this is not routine yet, but it will be in another decade or so. Lots of chemistry for both the atmosphere and ocean. Interactive biology on the land surface. So this means, of course, a variety of things, but it includes things like seasonal greening. So, you know, does my yard get green in the summer, or was it too dry? And also changes in species over century timescales, let's say. So deciduous forests perhaps migrating toward the pole. Interactive biology in the ocean is also interesting. First of all, it's interesting from the point of view of the carbon cycle. It's interesting because it affects the turbidity of the water, and that affects whether the sunshine that's absorbed by the ocean is absorbed in the top 10 meters or the top 50 meters, and that determines how much the sea surface temperature changes in a day. And also mixing is actually thought now that certain types of critters in the ocean produce a significant amount of mixing down well below the surface simply because the background mixing is otherwise so weak there. One slide about the future, and you notice I'm on thing number 10 now. So one thing that hasn't been done yet with a general circulation model, that is a comprehensive climate model of the type I've been describing here, is an actual simulation of ice age cycles, which are shown here, just a cartoon, but on time scales of, you know, let's say hundreds of thousands of years. This will happen probably within the coming 10 years. So it'll be an important test of the models, and it will probably make an impression on some people, but it hasn't been done yet. It's been done with much simpler models. Very high resolution models. This may look like a picture of the Earth, but it's not. This is actually a simulation, and the amount of detail in the simulation is far greater than what you can see in the picture. This is a calculation done in Japan, and the individual grid points in the model are only about 3.5 kilometers apart. So this type of model can actually directly represent the growth of larger clouds, like thunderstorms. And these models exist right now, but they're too expensive to run for a century. In fact, no one has even run one for a year yet with that type of resolution, but it's coming. In 10 years or so, we're going to see this. And finally, more interactive biology. I've described a little bit. Most of that is work in progress. There'll be a lot more of it. So there are people out there who would even like to put human beings into the model. And you can imagine the human beings in the model make decisions about how much coal to burn or you know, various other things. Okay. One slide to talk about prediction, because I'm about to describe some predictions made with the climate model. The first thing to understand is that predicting a change in the state of the climate is fundamentally different. It's not the same kind of thing as predicting the weather. The change in the climate is a forced change. It is analogous to the seasonal cycle. I can't predict, no one can predict the weather in Vancouver 2 weeks from now with any skill at all. but I can predict with great confidence that next July in Vancouver will be warmer than today. Okay? I can't tell you whether July 1 will be warmer than July 2, but July will be warmer in January. So, of course, you know this, but think about why is it possible to make that prediction, even though I can't predict weather 2 weeks ahead. The reason is that the seasonal change is brought about by the predictable movement of the Earth in its orbit around the Sun, and that produces the same sort of result every year. And that type of seasonal change, of course, is simulated by the climate models. I mean, that's a very basic test that was passed 30 years ago. But it's a forced change, and other examples of forced changes are the day-night cycle, the diurnal cycle, and ice age cycles, which I mentioned. And, of course, anthropogenic changes in atmospheric composition. That's a forced change. So, and volcanoes, if you know the forced change, volcanic eruption, large volcanic eruption, which we'll talk about a little bit later. So, the question is, has any climate model ever made a demonstrably successful prediction of anything? Okay, this is the abstract and title and so on from a paper published in January 1975 by these guys, Manabe, whose name I mentioned a little bit earlier, and Richard Weatherald. This is the first paper in which a coupled ocean-atmosphere comprehensive general circulation model, the type I described, was used to simulate the effects of doubling CO2. And so I yellowed part of the abstract here, but I've essentially transcribed this on the next slide, so let me cut over. In that paper, which you can get on the web, if you're sitting here online, you could probably get it before I finish with the next slide. It's available free of charge at the American Meteorological Society website. They predicted that the troposphere, the lower atmosphere where we live, would warm up, that this warming would be greater near the poles, especially the North Pole, that the stratosphere will cool off, we'll talk about this in a minute, and that there'll be more rain globally, not everywhere, but globally, and higher humidity overall, more water vapor in the air. All of these things have happened. So this was published 36 years ago. This is an example, you've seen things like this before, but the upper panel is global, and this is the difference in degrees C or Kelvin from an average from 61 to 90. So you can see the average is taken in here. And so these are positive to mean a warming relative to that average, and negative to mean a cooler temperature. And again, this is global. And what you can see is that the early period, this is the middle of the 19th century, the numbers are about minus 0.4, something like that. And by the time we get out to the early part of the 21st century, they're up around plus 0.4, something like that. So you're looking at a little bit less than 1 Kelvin, roughly 1 Kelvin warming in this global record. If we just look at land north of 65 degrees, you get this result, and the scale is different. So this goes from minus 4 to 2. This went from minus 0.8 to 0.8. So in the early part of the period, we have values a little bit larger, a little bit more positive than minus 1, somewhere around there. And by the end of the period, we're up around about plus 1.5. So roughly twice as much warming in the Arctic region as for the whole Earth. Manabe and Weatherall predicted that. The reasons for this I'll come to in a minute, but it's pretty obvious. Okay, one reason is sea ice is melting, and I know you had someone here earlier who was talking about this. So here the blue envelope shows predictions by models. This goes back to 1950. This goes out to 2050. The red curve is actual data for the Arctic out to sometime about 5 years ago, I think. And what you can see is that the models predicted a decrease, and there has been a decrease, but it looks like maybe it's faster than was predicted. We'll have to wait and see what happens. It might go back up. But certainly This means that the Arctic Ocean is becoming darker in the sense the albedo is going down, less solar radiation is being reflected from the surface, and that, of course, is a positive feedback. So I'm beginning to work my way into a discussion of feedback. It'll be sort of a gradual transition. This is the same kind of thing, ice extent versus time in the northern hemisphere. This is the number of square kilometers covered by snow in March and April in the northern hemisphere from the 1920 or so up to almost now. You can see a strong downward trend about the last 20 or so years. So again, this means an increase in the absorbed solar radiation, a decrease in the albedo. So let's talk briefly about forcing and feedback. I've already used the term forcing a couple of times. I said that climate change is forced, and so we have to distinguish between internal processes, which are part of the system, and I listed lots of those processes a few slides ago, and then external processes that are unaffected by changes in the climate. So the number one sort of gold standard external process is the sun. We don't think the sun really cares about anything that happens on this little planet. Volcanoes, of course, are really part of the Earth, and in some very long-term sense, they're part of the climate system, although not on century timescales so much. But they do predict fairly large changes produce fairly large changes in surface temperature in the timescale of a year or two. And then, of course, human influences. And you might also question whether this is really external. After all, we're part of Earth. But we'll treat ourselves as external here for purposes of this discussion. So forcing is due to external processes, and a change in the forcing can produce a change in the state of the system. And feedbacks are due to changes in internal processes. So let me go back a slide. Something like this is a change in an internal process. It affects the albedo and other things too, not just the albedo. There are other important differences there. But this is potentially producing a substantial positive feedback. And feedbacks enhance the warming. So I showed you earlier that with no feedbacks, and I explained what I meant by that, we would get 1.2 Kelvin for a doubling of CO2. When we put in the feedbacks, we get about double that. Okay? Now, I'm not saying that at the end of the 21st century, we're going to have, let's say, 2.5 Kelvin warming. I actually think it'll probably be more than that because we're going to go way beyond doubling CO2 by the end of this century. The albedo feedback involving sea ice and snow and so on is explained here, and this is very simple. It hardly needs to be explained. But suppose that you increase greenhouse gases and that leads to a warming. That will lead to a melting of snow and ice. That reduces the albedo and increases the amount of absorbed sunshine. That leads to more warming. So I put a big plus sign in the middle here to indicate a positive feedback. And of course, it can work the other way. You can have a positive feedback that takes you to a cold state because more and more snow and ice form as you descend into the cold state. We'll actually see this here in a few minutes. This is stratospheric cooling. Now, a few slides back, one of the things that I said that Manabe and Weatherall predicted was a cooling of the stratosphere. The stratosphere cools when you increase CO2. First of all, you have to know CO2 is extremely well mixed in the atmosphere. Okay, except very close to the surface in regions with a lot of vegetation, it's almost uniform. It hardly matters where you measure it. You can measure it in Mauna Loa or Vancouver or anywhere, and you get basically the same numbers. The stratosphere is way up there, close to space, so to speak, and it's relatively easy for an infrared photon emitted by gas in the stratosphere to make it out of space, to lose energy from the whole system. And so when you increase CO2, this sort of outer part of the system, the skin at the edge of space, cools off. And it actually cools off, according to the models, it cools off quite a bit more than the surface warms up. This is a bigger signal. And a bigger signal is, of course, easier to detect. So this is one of the predictions in the Manabe and Weatherall 1975 paper. This is actual data from the 60s out to essentially now. And we're not going to look at all of these panels, but this is the lower stratosphere. And you're seeing, with the exception of these spikes, you're seeing a decrease in the amount of, in the temperature of this region on the order of, I don't know, from about 1 down to about minus a half or so, so 1.5 Kelvin or so over a period of about 50 years. These spikes are due to major volcanic eruptions. When a big volcano goes off, like in this picture, it blasts debris into the stratosphere, and that debris actually absorbs quite a bit of solar radiation. So the stratosphere warms up. But because that sunshine doesn't make it down to the ground, the Earth's surface actually cools off for a couple of years in a big volcano like Pinatubo, which is, I believe, what this is a picture of. And so one way that the models are actually tested nowadays, this is fairly routine, is when a new volcano goes off, before the real Earth actually changes, the models are used to make a prediction of what the cooling of the troposphere and the warming of the stratosphere will look like. And so that's something that was started by Jim Hansen when Pinatubo exploded. Manabe and Weatherall predicted an increase in rain and humidity. The term humidity is kind of vague. What this shows is measurements of the column water vapor. This means the total amount of water vapor in the whole column of air. We usually call it precipitable water, which is a kind of a weird name, but it's like kilograms per square meter. Okay. And the measurements that you see in the map up here are plotted only over the ocean because the method used involves microwave radiometry from space. And when you look down at the land surface, the emissivity in the microwave is very complicated, and you can't do the retrieval. People are trying, but here we plot the data only over the ocean, and the red colors mean more water vapor, and the blue colors mean less. And you can see, with just a couple of exceptions, it's basically all red or yellow. And this is global mean over the ocean plotted in a simple way over time. You can see the linear trend fitted there. These are measurements of precipitation over land. There are similar measurements over the ocean done from satellites, which I won't show here. But basically, this shows changes from the beginning of the 20th century. Satellites didn't exist then, out to about now. And the greenish colors are increases in rainfall, and the brownish colors are decreases. And you can see both colors in the picture, but overwhelmingly there's an increase on the average. So let's talk about the water vapor feedback, and this is actually one of the things I was asked to talk about here. So I'm going to slow down a little bit, see what time it is. This is a very simple idea. Diagram just like the one I showed you for snow and ice albedo. Suppose we increase greenhouse gases and this leads to a warming. That will tend to produce an increase in the amount of water vapor in the atmosphere. It does so in the comprehensive models, and you can produce simple arguments that it should, because as the ocean warms up, the saturation humidity at the sea surface temperature and surface pressure increases very quickly, exponentially, basically. And using the current climate as a baseline, in the warmer parts of the Earth, the tropics, the rate of increase of the saturation vapor pressure with temperature is roughly 7% per Kelvin. 7%, 1 Kelvin. Really, really fast. And it just keeps getting steeper. So, an increased amount of water vapor in the atmosphere strengthens the water vapor greenhouse. Water vapor is a very strong greenhouse gas. And in terms of mass, there's roughly 4 times as much water vapor in the air as there is CO2. Okay? So this would strengthen the warming, and I put a big plus sign in the middle to indicate a positive feedback. Of course, the feedback, again, could work the other way. If the planet was cooling off, the amount of water vapor in the atmosphere would decrease, and that would allow a further cooling. Okay? So here's something I mentioned at lunchtime in a conversation with some of the folks here. This is from a paper by Andrew Lasis and colleagues in Science late last year, November, I think. And so what they did, a very simple thing, as far as I know, nobody had ever done before. And they did this as a kind of tutorial exercise. They knew what they would get. They at NASA Goddard Institute for Space Studies in New York City, they have a climate model. They've had one for a long time. And they ran the model into a statistical equilibrium for the current climate. So we're not talking about greenhouse warming, just current climate. And at a certain time, time zero in this diagram, they removed all of the CO2 and all of the methane and all of the CFCs and nitrous oxide, all of the greenhouse gases from the atmosphere, except water vapor. They just zeroed it out. And this is what happened. So here's the surface temperature, and that's the black curve. So it goes from something like 14 or so Kelvin down to minus 20 or minus something like that. And it goes down really fast. Column water vapor. This is the most important curve, really. Look what happens. It takes a dive. That is plotted in percent change, I believe. So it goes down to roughly 10% of its initial value. So what's going on here? Well, it's this in reverse. We decreased the amount of greenhouse gas. We just got rid of all of it except for the water vapor. That led to a cooling. That led to a decrease in the amount of atmospheric water vapor. And water vapor is a greenhouse gas, so we got a further cooling, and that led to even less water vapor, and we fell off a cliff. You can see the increase in sea ice cover, the increase in the planetary albedo. The planet gets cold in a hurry. So it's true that in the current climate, water vapor is the most abundant and radiatively the most important greenhouse gas. But water vapor is condensed. It does it all. It's doing it right outside, right now. So CO2 doesn't do that on this planet. It does it on Mars, but it doesn't do it on the Earth. Nice little experiment. Cloud feedback. This is a huge subject, and I'm going to explain it in very simple terms, but if we have questions, I'll go into it in more detail. There's a paper published in, I think, the mid-'70s by Stephen Schneider, who many of you will remember died not long ago. He's a very outspoken climate change person who's written a number of popular books on the subject. And he was not really a cloud guy, but he wrote a paper that's widely cited because it was one of the first, and he pointed out that when you think about how clouds affect climate, the three big things that matter are the cloud amount, obviously. So this refers to how many square kilometers of the planet are covered by cloud. The cloud top height. High clouds do one thing, low clouds do another, as I'll explain in a second. And then the optical properties of the cloud. So this has to do with how much liquid or ice is in the cloud, but it also has to do with how that mass is distributed. If you put the mass into a very large number of small particles, you get more optical bang for your buck than if you put it into a smaller number of larger particles. Same mass. So adding more low clouds, so this means increasing the cloud amount for low clouds. And this is a picture of low clouds over the Atlantic from a paper that I just reviewed a few days ago. And you may never have seen a picture like this, but it's really quite amazing. The scale of this would be several hundred kilometers on the side. The dark areas, you're seeing the ocean. The light areas, you're seeing the cloud, and you can see these little geometrically looking cellular shapes in there, which are distributed in a very complicated but somewhat orderly way. And this is extremely common mode of low cloudiness. But at any rate, the point is, these guys are bright. The albedo of a low cloud like this is typically something like about 45 or 50%. So it'll reflect roughly half of the solar radiation that hits it back to space. So when you add more of this type of cloud, and these clouds are down near the surface, so they don't, so they have a temperature that's not that different from the surface temperature. So when they emit, if you think of them emitting as a black body, which is not far from the truth, they're emitting at almost the same temperature as the surface anyway. It doesn't have that much of an effect on the infrared going out of the top of the atmosphere. So adding low clouds cools the planet because they have a big cooling effect in the solar radiation and they don't do much to the infrared. High clouds tend to warm the planet. So in this picture, what you're seeing is an infrared image. It's an instantaneous photo, not a time average or anything. And you're seeing a storm up here in the North Pacific. This is North America. and some other features like that. So these are high cold clouds, and they're black because they are not emitting much infrared, and this camera is capturing infrared. Of course, some high clouds are bright, but a lot of cirrus clouds are rather transparent. In some overall sense, the effect of the high clouds on solar radiation is less than the effect of the low clouds per unit area, let's say. But their effect on the infrared is much more because they're so cold. So, for example, if you have warm water, this is a high cold cloud down in the tropics someplace. The water underneath there might be at a temperature of, 290 or something like that Kelvin. But the top of this cloud is at a temperature of about 200 Kelvin. And remember, the emission goes like temperature to the fourth power. So the emission from the top of this cloud is rather weak compared to the emission from the ocean. The infrared that's coming up from the ocean gets absorbed. That energy is trapped in the system below the level of the cloud you see in the picture. So adding more of this type of cloud warms the planet. If you take away low clouds, you'll warm the planet. If you take away high clouds, you'll cool the planet. So all kinds of stuff can happen here. And I'm only talking about two types of clouds as if that's all there are. And of course, that's not right. So this is pretty complicated. There isn't one cloud feedback. There are many cloud feedbacks. And they're different in different parts of the world. There are clouds over the sea ice in the Arctic. So low cloud feedback would work something like this. Same format as before. Increase greenhouse gas, produce a warming. Suppose that led to more bright low clouds. Then we'd have less absorbed sunshine, and that would mean less warming, a negative feedback. But I just said suppose, because it could be less bright low clouds. And what the models are actually predicting is less. These are observations. This is not a model result. These are from Conway, Leobe, and Joel Norris. This paper published back in the early 90s. So the upper panel shows a trend in low cloud over the ocean, nothing plotted over the land here. And this is based on surface measurements, basically. And in this figure, red colors mean a decrease in the amount of low cloud. Blue colors mean an increase. The lower panel shows the change in sea surface temperature over the same period. And what you see is that in places where the sea surface temperature increased, that's red colors, I had less low cloud. Where the sea surface temperature decreased, I have more low cloud. Now, cause and effect is not so simple here, and I'll tell you why. This type of cloud likes cold water. So if you warm the water up, that by itself will tend to decrease the cloud fraction, the amount of the cloud present. And that does sound like a positive feedback for warming, doesn't it? So it may be that the stratus decreased because the surface temperature warmed up, or it may be the other way around. The surface temperature warmed up because there was less stratus. And in fact, it can be both. That's the nature of the feedback. High clouds. Well, I've really already explained this, but let's just go through it. Increasing greenhouse gases, a warming. If we have more high cold clouds, that'll be less infrared emitted, and that'll reinforce the warming, positive feedback, but it could go the other way. These are actual feedbacks produced by climate models in the fourth assessment of the IPCC, which is published in 2007. So this is a figure from the book, and this is also available online for free. You can buy it in the bookstore, but it's out there for free online. So this is not a graph exactly. The different positions along the horizontal here are different types of feedback. And on the vertical axis, we've got a feedback parameter. The units are watts per square meter per Kelvin. Watts per square meter is energy flow per Kelvin. Change in energy flow per Kelvin. So it does sound like a feedback, right? And so what we got here is water vapor, clouds, albedo, so this means snow and ice albedo. Lapse rate, which I'm not explaining here, it's a little too technical. If there's a question, we can talk about it. This is the combination of water vapor and lapse rate, and this is everything together. And what you can see is, first of all, the total feedback is positive on the order of 2 watts per square meter per Kelvin. So if I got a 2 Kelvin warming, it'd be 4 watts per square meter, right? And where does that come from? Well, the only negative contribution really is the lapse rate feedback. Maybe I'll explain what that is, but I don't have a slide to show you. Let me just wave my hands. Lapse rate is jargon for the rate at which temperature decreases upward. So you're driving uphill into the mountains, it gets colder. Okay, so the rate at which the temperature decreases upward is called the lapse rate. And for rather simple physical reasons that are pretty well understood, the lapse rate is predicted to get smaller in the future climate. And this is not just greenhouse warming. Any warming of the Earth due to any reason, like coming out of an ice age, the lapse rate is expected to get smaller. And what that means, since the lapse rate is the upward decrease of temperature, is that the warming is actually greater some distance above the surface than it is at the surface. Well, if you're some distance above the surface, it's easier for the infrared photons to get out of space, right? It's like the stratosphere, not all the way in the stratosphere, but you're higher. Same idea. So decrease in the lapse rate, which is what's expected from a warming, is a negative feedback for that reason. Makes it easier to cool the planet off. But the rest of them are basically positive, and the total turns out to be positive. This will be done again. You may not see the same kind of figure, but it will be done again in the ongoing 5th assessment of the IPCC. Let me mention that this diagram doesn't show all of the important feedbacks. It doesn't show feedbacks due to biogeochemistry, things like changes in the amount of carbon, let's say CO2 and methane in the air that come from thawing of the permafrost. Okay? It doesn't show changes that come from fluxes of CO2 out of the deep ocean, the southern hemisphere. And it also doesn't show the melting of the big ice sheets on the continents. And that's because that melting will occur on timescales of hundreds of years, and these are just essentially 21st century runs. The melting of the ice sheets, I personally believe, is bound to be a positive feedback. I don't see how it could not be. And it'll kick in a little later, so it'll make this number go up. And probably the thawing of the permafrost is a positive feedback too, and there's reasons in paleodata to believe that the carbon fluxes are positive feedback. So the estimate of feedback here is valid on relatively short timescales on the order of a century, but probably an underestimate of feedback on timescales of several centuries. So my last slide, so just a summary, the reasons to expect global warming from an increase in CO2 and methane and so on are not complicated and not controversial. They can be summarized literally on the back of an envelope. In fact, I have written them out in small handprint on the back of a business card. Okay, it doesn't even have to be an envelope. The comprehensive models that we use to make more detailed predictions have existed since the early to mid-60s and are under intensive development at a lot of centers around the world, mostly laboratories. A few university groups like mine are doing this. The net effect of the many feedbacks in the climate system is to amplify the warming relative to what would occur without feedback, and the most important single amplification comes from water vapor, and probably the second most important one is snow and ice albedo, especially if you live near the North Pole. But others are important, and it looks like the cloud feedback is probably positive, but not as strong as water vapor or snow and ice. I'll stop there.
The one thing in your talk that surprised me, and surprised me a great deal, has to do with the low clouds. I would have thought, in the same spirit as your back-of-the-envelope calculation, that if the temperature rises for any reason, the cause is not important, evaporation rates will go up, therefore there'll be more clouds, which causes more reflection and therefore provides a negative feedback. So why doesn't it work that way?
Well, the increase, lots of things can happen to that water vapor. Okay, and one of the things that can happen is that it forms a kind of uniform stratus cloud like the ones I was describing. Another thing that can happen is it makes shallow cumulus clouds, which have a much smaller cloud fraction. As you go from, let's say, the west coast of North America down towards Fiji or something, in the deep tropics, as the sea surface temperature increases, you get a transition from kind of overcast low cloud to shallow cumulus, and the cloud fraction goes down from 95% to 15%. So the form of the cloud changes dramatically, and those convective clouds in the lower latitudes have the effect of carrying water vapor up, so the humid layer gets deeper, but the cloud amount is still rather low. And further downstream towards Fiji, let's say, you get you rain out a lot of that water vapor in the big thunderstorms in the deep tropics. So there's not a simple increase in low cloud amount that comes from more evaporation from the ocean. It just doesn't work that way. I mean, there's a logical disconnect between more evaporation and more low cloud. It doesn't compute.
Is there a significant difference in this respect between ocean clouds and land clouds?
Yeah, there are lots of differences between ocean clouds and land clouds, and a lot of it has to do with the fact that over land the temperature changes by a lot between day and night, virtually every day, whereas over the ocean the sea surface temperature hardly changes at all in one day. So over land the clouds are getting pushed around big time by the changes in surface temperature, and over the ocean they don't have that problem. So things over the land are considerably more complicated. You may have a tendency to low, foggy cloud in the early morning, just before sunrise, and thunderstorms in the afternoon. That's the sun going up and down that does that. It doesn't work that way over the ocean.
Norma.
You had one slide there that Lee was referring to, I guess, on the regard to the low-level cloud and high-level cloud. Is there good data available going back very far on the extent of the global cloud cover at both low-level and high-level?
Yeah.
And how far back does it go?
It goes back.
The second question,
okay.
or I'll wait till you answer that one, perhaps.
Okay. Yeah, I'll probably forget your first question if we take the second. The data, of course, there's some data going back into the 19th century, let's say, but reasonably complete data on cloudiness worldwide, or almost worldwide, goes back to around 1950 or so, and obviously that's not satellite data, it's surface-based data, and people are still collecting that type of data today. The satellite record starts in the 70s and became pretty good in the early 80s. So if we just take the satellite period, we have about 30 years or so of very good data. Now, there are problems with both the satellite and the surface data. The satellite's looking down, so it can see the high clouds, but it might miss the low ones if there's a high one in between. Opposite case if you're a surface observer, right? So there are technical issues with both, but we've had both for about 30 years. And combining the two types of data allows you to resolve that kind of issue pretty well.
The second question concerns the formation of clouds. You've mentioned some factors, and humidity and so on. Does the sun play any role, directly or indirectly, in the formation of cloud cover?
Well,
in your opinion?
Clouds are mostly produced, for example, the ones outside today, are produced because the air is going up. That probably sounds weird. The air is rising because we're in a certain part of a storm system, and the storm causes the rising motion. As the air rises, it's moving to lower pressure. It expands adiabatically. That causes it to cool. As it cools, the saturation vapor pressure goes down. And so you get at some point, if you cool it enough, you'll get condensation and a cloud is produced. Now, of course, the cloud droplets are nucleated on aerosols, and the presence of aerosols in charged aerosols in particular can be of interest in this context. And there can be solar influences and cosmic ray influences on the availability of the nuclei on which the cloud particles are formed. But down here in the lower atmosphere, the presence or absence of clouds is never conditioned by the availability of nuclei. There's always plenty of nuclei. The presence or absence of clouds is basically produced by how the air is moving. In the upper troposphere, it's easier to find situations in which the availability of nuclei is less, and there's more potential for changes in cirrus cloudiness associated with changes in the availability of suitable ice-freezing nuclei. But throughout most of the troposphere, the availability of nuclei is just not an issue. Now, it does matter for how the mass is distributed. I mentioned this briefly as I went through. Let's say I have 1,000 kilograms of condensed liquid water in a certain area. It's in a cloud. If I put all of that liquid water into 10 micron drops, those are rather small drops, I'll get a really big effect on the solar radiation, assuming the sun is up. If I put the same mass of water into 50 micron drops, I get less of an effect on the solar radiation. The size of the drops on which that 1,000 kilograms or whatever I said of water is distributed is strongly influenced by the number of nuclei present. So in polluted air where there are more nuclei, you'll tend to get brighter clouds. In clean air, you'll tend to get less bright clouds. So the nuclei do have some important influence on the cloud optical properties, but they don't determine whether clouds are going to form or not in any important way in the troposphere.
Stop. David will be available in the Irmax boardroom, I think at 2 o'clock. Is that right, Colin? Almost immediately. So those who are interested in more in-depth discussion, by all means, join him there. And let's thank him once again.